Hello everyone, myself Sai Prachi Satabdi, roll number 23ME 30048. Before we begin, I would like my teammates to introduce themselves.
My name is Saya Baya, roll number 23ME10016.
My name is Akshaya. My roll number is 23ME30068.
I am Zormista Murmu, roll number 23ME 30054.
Together, we will be presenting the windscreen wiper mechanism as a part of our mechanism sessional ME29002 tutorial 5.
So our problem statement is synthesize and make a simulator for the windscreen wiper mechanism shown in tutorial sheet 2 question 6 with no quick return effect. In this simulation, mark the area wiped. Given O2AbO4 is the 4-bar mechanism. O2 is the crank. O2A measures 30 mm. AB is the coupler. AB measures 200 mm. O4B is the rocker. O4B measures 80 mm. CO4 measures 300 mm. DO4 measures 300 mm. Delta is the angle. It measures 10 degrees. Assumed CD equal to 100 mm. If the sum of the shortest and longest link is less than or equal to the sum of the remaining two links, then the mechanism satisfies the Grashof criterion. Here 330 plus 200 less than or equal to 80 plus 158.11. So this satisfies the Grashof criterion.
Let's take a look at how a simple mechanical arrangement powers the wiper motion we see on a vehicle windshield. I would like to start with the basic idea of the wiper mechanism. The windscreen wiper mechanism works as a 4-bar crank rocker system. In this mechanism, one link rotates continuously like a crank, another link transfers this motion, and the final link oscillates back and forth like a rocker to create the sweeping motion of the blade. All of these are connected by fixed pivot points on the vehicle frame. This setup converts the steady rotation from the motor into the smooth back and forth wiping action needed to clear the windshield effectively. Moving on to the next slide, why the crank rocker mechanism is ideal. The crank rocker mechanism is ideal for windscreen wipers because it turns uniform motor rotation into smooth oscillatory motion using just a single degree of freedom. With the correct link proportions, the forward and return strokes happen at almost the same speed, giving a clean and consistent wipe. It is compact, uses simple revolute joints, and has very low friction and wear. This simplicity and reliability are exactly why the crank rocker design is widely used in automotive wiper systems.
Now moving on to the Grashof criteria, the Grashof condition help us to determine whether a 4-bar linkage will allow any one of its links to rotate continuously. In a 4-bar mechanism, we label the shortest link as L, the longest link as L, and the other two links as P and Q. According to the Grashof criteria, if the sum of the shortest and longest links, that is S plus L, is less than equals to the sum of the other two links P plus Q, then the mechanism is Grashof. This means a crank can exist and continuous rotation of one link is possible, which is essential for a motor driven system like a wiper. If the criteria is not satisfied, then no link can rotate fully and all links will only oscillate. Such a mechanism would not be suitable for a wiper drive powered by a continuously spinning motor.
In the next slide, we discuss the quick return effect. This is a behavior seen in some 4-bar mechanisms where the output link moves faster in one direction and slower in the other, resulting in unequal forward and return strokes. For windscreen wipers, this is undesirable because we need smooth and uniform motion in both directions to clean the glass effectively. In our crank rocker mechanism, the link proportions are chosen carefully so that the rocker's angular momentum remains almost symmetric for equal crank rotations. This effectively eliminates the quick return effect. As a result, the wiper blade sweeps the windshield evenly on both the forward and return strokes, ensuring consistent and reliable cleaning performance.
We obtain the displacement equation where A, B, C are function of length and angles. The displacement equation obtained is a result of equating the magnitude of the vector L2 to L4 with the length L3. Upon time differentiating the displacement equation, we obtain the velocity equation where J is known as Jacobian, which is a function of length and angles. Further time differentiating, we obtain acceleration equation.
In, in the next slide, we present an analytical torque analysis. Here we assume that the wiper blade experiences a constant friction force as it presses against the windscreen with nearly uniform pressure. This creates a constant resisting moment on the output link shown as tau 4. Using the principle of virtual work, the input and output work must balance, which gives us the relation tau 2 delta theta 2 is equal to tau 4 delta theta 4. From this, torque transmission reduces to tau 2 is equal to J into tau 4, where J is the mechanical advantage or Jacobian of the linkage. The expression for theta 4 and the Jacobian J shown here relate the angular velocities of the input and output links based purely on geometry and instantaneous configuration. This analysis helps us understand how torque varies through the wiping cycle even though the blade load remains same.
We have used MATLAB for this simulation. This MATLAB program simulates the complete motion of a windshield wiper mechanism using a realistic 4-bar linkage model. The code continuously calculates the position of each joint, checks for impossible or unstable movements, and automatically corrects minor numerical issues so the animation remains smooth and accurate throughout the simulation. On the left side of the slide, we see the real-time animation of the crank, coupler and wiper link moving through a full wiping cycle. The blue shaded region represents the swept area on the windshield, while the marker at the tip traces the exact path followed by the blade as it moves. In the tip speed versus time graph, the speed increases smoothly, reaches a peak, and then drops to nearly zero at the turnaround points. This happens because the mechanism has to reverse direction, causing a brief slowdown. In the acceleration versus time graph, the high acceleration peaks occur during the rapid deceleration and reacceleration phases as the blade switches direction. Between these reversals, the acceleration stays relatively smooth, reflecting stable and consistent sweeping motion.
Concluding, the windscreen wiper is a simple 4-bar crank rocker mechanism. A steady motor rotation is converted into a smooth back and forth sweep by choosing the right link lengths and meeting the Grashof condition. Torque and sweep analysis show how the load changes through the stroke and how the blade efficiently clears the required area. Thank you.